This conference will now be recorded.
This conference will now be recorded.
Shivam, you are using a mobile internet or Wi-Fi?
Wi-Fi.
सिग्नल स्ट्रेंथ कैसे है? सिग्नल स्ट्रेंथ
क्या बोले?
अरे यूज ईयरफोन्स.
Earphones. Hello.
Fine. Now it is okay.
Okay, so now you're able to see the slides.
No यार स्लाइड्स डिसेबल हो गया था वो. फिर से करो.
Slides not there, not there.
Slides.
Slides not there.
No.
I am slides.
Share screen. Share screen. Now the slides are visible.
Okay.
Yeah, Chandrasekhar sir, are you in online?
Yes.
Hello, sir.
Sir.
Hello. Yes.
Chandrasekhar sir, yeah, you can start the introduction.
Okay, sir. Good morning to all the participants. Thank you for joining the Day 5 online faculty development program on current research trends in electronics and communication engineering. Myself, Chandrasekhar, Assistant Professor in the Department of ECE, RGM Engineering College, and Coordinator for this event. It's my privilege to introduce today's speaker, Dr. Shivam Verma. He completed BE from Sri Vaishnav Institute of Technology and Science, Indore, in 2010. M.Tech from Indian Institute of Technology, BHU, Varanasi, in 2012. PhD from Indian Institute of Technology, Roorkee, in 2017. He published 8 high-quality papers in IEEE transactions on magnetics, IEEE transactions on nanotechnology, IEEE transactions on electronic devices, IEEE transactions on VLSI systems. He previously worked in BITS Pilani, Goa, NIT Warangal, and currently is working as assistant professor in the Department of Electronics Engineering, IIT BHU Varanasi. He is currently working on one sponsored project funded by DST SCRB on development of simulation software for Spintronics device and circuit simulation. His research interests are Spintronics, magnetic tunnel junction, mixed mode signaling. If any queries, please do not interrupt the presentation. You can raise your queries in the chat box. These queries will be answered at the end of the session. Once again, a hearty welcome you all to this program. I hand over the session to Dr. Shivam Verma, sir.
Okay, thank you. So, am I audible? Hello, sir. Shall we start?
Yes,
Yes, sir, you
please
can
continue
start, sir.
that.
Okay. So, thank you for the introduction. So, basically, I will give a brief idea about spintronics and how spintronic devices can be used to transform the computing architecture that we are using conventionally. So, let me begin with what is spintronics. So it is emerging technology that uses both the spin orientation of an electron as well as its associated magnetic moment. So electron, by virtue of its motion along its own axis, has a magnetic moment associated with it. So you must have seen that electron orbits around the nucleus. So that is one motion of an electron. Another motion of an electron is the electron orbits around its axis also. That is the spinning motion of the electron. That so both of them contribute to magnetic moment. But what we are talking about more in our field of spintronics is the spinning magnetic moment. So because of the spin, there is an angular momentum associated with the electron, and because of the angular momentum, there is a magnetic moment. Because electron is a charged particle. So if it does not have any charge, then there will be no magnetic moment. But since it is having a charge which is equal to the charge of a proton, that there will be a magnetic moment when it spins around its own axis. Now, spintronic devices basically require two things. They
Shivam,
require generation and manipulation of
hello,
population.
Shivam,
Yes.
Shivam. Hey, we
Hello.
are getting disturbance.
Yes.
We are
Yes.
getting disturbance actually. Disturbance in your voice.
Yeah. Disturbance.
Ah,
I
so
don't
we
know.
have to see
Rectify
the
that.
alternative.
Huh?
So,
Online video
so
I should close.
no, you remove the earphones and you can try for once. We will check whether the voice is clear or not.
Just I'm closing my video. I think that will be better. So am I audible now?
Little better. We will check. We will check. So you explain one slide and we will see how your voice is.
Okay. So as I told you that the spintronic device requires a generation and manipulation of spin polarized population of electrons. So the we are not talking about only a single electron here. We are talking about a whole population that we will use for generation and then manipulation of information. So the physics of all spintronic devices that generally revolves around a specific kind of material, which is commonly known as ferromagnetic materials. Now, if you know about ferromagnetic materials, uh, they are generally the transition elements that are found in the periodic table. So we'll come back to the ferromagnetic materials. But before we move to the ferromagnetic materials, let us just discuss about what is the motivation behind spintronics and why we are so hell bent on doing something uh, which uh, which is like which involves the spin of an electron. So Let us begin with the common general computer architecture that we are having in our normal laptops or desktops, or we can say any high-end workstation. So we have now modern processors have a number of different cores, which are individual processing units. So these cores are where these we perform the arithmetic and logical operations, and their memory and the logic they are separate, and you can see that all the core and this uh, there is associated L1 instruction SRAM and L1 data cache SRAM. So all these we can say registers and instruction RAM, these are all in logic. Now, after logic, we have a three levels of memory hierarchy, which involves we can say L2 cache, then L3 cache, and then followed by main memory. So the hierarchy also goes further high with two other levels of memory, which are secondary stage and tertiary stage. So if you see these secondary stage and tertiary stage, these are generally the non-volatile memories where the data stored is saved or is kept saved even if we turn off the power. But all these memories which are there between L2 to main memory, and including the instruction, we can say registers and the instruction SRAM, all the memories that are till here, these are all volatile. It means that if you turn off the power, the data in those, we can say the data that these memories stores from from L2 cache, L3 cache to main memory, the data is lost. So you can, what happens is, if we are turning off a computer, then the data gets lost, and when we turn it on again, the data has to be transferred from the secondary and tertiary storage back to the main memory and cache in order to perform our regular operations. So this normally happens in the process of booting that you do in your, we can say, computers. So now this whole process of booting consumes a lot of power, and also you generally do not want to turn off and turn on your system again and again because of this reason. And when you keep your system turned on, then you will lose power. So that is why you can say that general computer architecture is power hungry in nature. And in the second figure, the memory hierarchy is given. You can see that this here you have again ALU, that is which is part of the chip, register files which are all part of the chip, L1 cache which is also part of the chip processor core of the processor. Then we have cache RAM, which is a part of the CPU. So the again you can see that the memory hierarchy by generally is represented by this kind of a triangle. So because the and this is also this is basically a trade-off between cost and performance. So that is why we cannot have all ALU or all cache in a computer, because ideally we would want a fast memory to be present in the computer, but the fast memory is also costly. And if you use only a costly memory, then your uh, the computer or desktop, which is a general purpose device, it is only costing 50,000. It may cost in crores if you are using only a cache memory. That is why we cannot use that, because common public cannot use it if we have such high costs. So that is why we use a trade-off between a low cost and high cost memory. Generally, the low cost memory is non-volatile, but it is having a very slow access time around of zero point 0.1 to 100 milliseconds. As we go up in the hierarchy, we can only have a smaller memory, because again if we try to have a bigger capacity, then the cost increases. So this is the trade-off between we can say performance and cost. So that's why we generally use kind of a hierarchy in a computer. and we cannot use a single kind of memory in the computer which is fast. So now the problem lies that all these memories are non-volatile except the secondary or non-volatile storage, which is hard disk drive or flash memory. The main memory, which is generally consists of DRAM, this is also volatile. SRAM is also volatile. So this way we have lots of non-volatile memories, and that is a bottleneck towards further reducing the power consumption in a computer. So now what is the spintronic devices, the are something which can lead to different kinds of architecture, where we can go for something called as the rectangular memory hierarchy. So instead of triangle, you can get a rectangular memory hierarchy if you are successful with spintronic devices, because they are non-volatile in nature. So if you have a case where you have L1 cache and L2 cache, instead of using the SRAM, you use a fast Magneto-resistive random access memory, which is consisting of a spintronic device. Then again, L3 cache also, if you use a, we can say, a non-volatile memory, which is again a spintronic based memory, then you can have something very useful for you, which is you can go from deep sleep to state to power on state very fast. So deep sleep state to wake up state in only 1 microsecond, which is just like you press an enter and you get the power on. Your application will also be there and you can start working. So this is all the motivation behind the going for spintronic devices, because they will lead to non-volatile memories and a non-volatile computing architecture, which can have a even a normally on system, or we can say which will be a normally off system. Just you press an enter and it will turn on, instead of the current system which is having a normally on nature, which you do not want to turn off because you will lose your application. You have to save your data to the secondary memory, otherwise you will not be able to get it again. So the conventional bottlenecks can be removed by using this. Of course, the long term motivation will be to keep everything as non volatile. So currently what is happening is we are proposing only in a short term objective is to use the conventional L1 cache, which is SRAM, and registers which are also CMOS based. But in distant future, people are trying to completely replace the capabilities of CMOS with a different kind of device, which is called as all spin logic device, which can be used and which is completely non-volatile. So instead of only memory, the logic will also be non-volatile. So this is the long-term motivation behind doing spintronic devices. So as of now, people are mostly working on the short-term motivation and have achieved STT RAM, which is capacity of around 1 megabits and or 1 gigabits also have come. But still work is going on. So let us move towards the early spintronic history. So how this the we can say field of spintronics evolved. So these are I have listed of a few of the monumental, we can say, achievements which I am going to discuss. So in 1985, the Johnson and Silsby, they we can say achieved something which is called as spin polarized electron injection from a ferromagnetic material to a normal metal. So there is a we can say a junction between two elements. One of them is a metal which is ferromagnetic in nature, and one is the normal conventional metal like copper or aluminum. Then when these are when a metallurgical junction is formed between these two, then the Johnson and Silsby observed that spin polarized population of electron can be injected into the normal metal. So the second most important discovery was the giant magneto-resistance effect, which was in 1988 by two groups in France, one in France and one in Germany. So these Fert and Gruber also have got the Nobel Prize for discovering giant magneto-resistive effect recently, I think in 2008. Then followed by, there is one more discovery that is very important in 1996, which involves the you can say discovery of spin transfer torque effect or mechanism, which is the magnetization switching by so you can store the information, but how do you manipulate it? So in 1996, people started to do this work. We'll discuss about spin transfer torque further. Then in 2006, they started to demonstrate how we can manipulate information electrically using spin transfer torque in magnetic multilayers. So these are a few of the monumental discoveries. I have also listed out the papers that are there. That the 1985 paper. Then you have the 1988 and 1989. So these two are basically just associated with the giant magneto-resistive effect. Then John Slavinsky's paper of 1996 and Magnus' paper of 2006. So these were the early discoveries that we can say are the pioneering works in the field of spintronics. So just still from this Google Scholar, you can see that this is a Nobel Prize work, and it is having some 11,000 citations. And so this is all three are having very high citations. This is giant magneto-resistance effect was discovered by them and published for the first time. So, so now we will move on to the main topic: how do spintronic devices work? And so, electron basically, by virtue of its spin, as I told you, has a resultant magnetic moment. So, electron is spinning around its own axis, and because of that, it has an angular momentum, and opposite to the angular momentum, you will have a magnetic moment, which is determined by this expression, which is, you can see that mu is the magnetic moment associated with electron of s. S may be plus half or minus half, and depending on s, the direction of mu will also change. So the angular momentum associated with a self rotation, this is called this is a magnetic moment basically. So angular momentum will be the minus of that. Uh, Now this gamma is called the gyromagnetic ratio, which basically relates the two things: electron spin angular momentum with the magnetic moment. So these are the few things that we already have studied in high school and higher secondary physics. So the response of any material to magnetizing field is generally called a magnetic induction. So, and the relationship between B and H is a property of the material. So you must have studied about the hysteresis curve of ferromagnetic materials. So whenever a ferromagnetic material is subjected to magnetizing field, you some magnetic induction is induced in it, and that magnetic induction that is proportional to the applied field. So based upon this, you have studied about a BH curve and how the residual magnetism comes in the ferromagnetic material. So in some materials in free space, B is a linear function of H, but in general it can be a more complicated, and sometimes it cannot be even a single value. But we use generally for a linear function of H. So you can see that there is one more term that is coming up, that is in the relation between B is equals to mu 0 into H plus M. So here mu 0 is the permeability of vacuum, magnetic permeability of the vacuum. H is the magnetizing field or the magnetic field that is applied. and M is the magnetization. Magnetization is the magnetic moment developed per unit volume. So you can see magnetization is basically magnetic moment. So individual moments are there in an atom. So when we have all these magnetic moments per unit volume, that is called as the magnetization factor. So, and then we have a magnetic susceptibility term, which is called the ratio of the magnetization to the magnetizing field H. So all these terms you already know, just you have to brush up these things. So when you see that what is we can compare the materials which are there in periodic table: diamagnetic, ferromagnetic, and paramagnetic. So diamagnetic are those which are having very low susceptibility, and also they are weakly magnetized in the direction opposite to the magnetic field. So if you apply a magnetic field in certain direction, they will be magnetized in the opposite direction. So that is having a susceptibility of 10 to the power minus 5 and negative. Then paramagnetic also have magnetization which is very small. I should say, or I should say, susceptibility is very small. So they are weakly magnetized, but in the direction of magnetic field. So, so our main focus in the spintronic devices are this ferromagnetic materials, which have magnetic susceptibility of 10 to the power 2 to 10 to the power 5, and they basically are permanently magnetized in direction of the magnetic field. So whenever you apply a ferromagnetic material with a magnetic field, it turns into a magnet basically. So it will have its north pole and south pole, and it will have its own magnetic field, which will be the closed loop. So moving further, so what are those ferromagnetic materials? I should focus at. So mostly this highlighted in pink. These are generally ferromagnetic in nature, but again not all. They are ferromagnetic in nature in this region because they have unpaired d electrons and in their orbitals, and these d electrons contribute to the magnetic moment. So because of the unpaired electrons, large number of unpaired electrons in the d subshell, which has 5 orbitals, you can have a large number of large magnetic moment associated with individual atoms. So then what? Let us basically ferromagnetic materials have a built-in magnetization even in the absence of external magnetic field. So once you have magnetized it, even if the magnetic field is removed, it will be magnetized for a long time. Okay, so next they have a non-equilibrium concentration of spins in conduction band due to the exchange split d subshells. So when we see the energy versus DOS curve of a ferromagnetic, we can say ferromagnetic material, there is a non-equilibrium present. So for example, in a normal material, we have, when we plot density of state versus E along, so energy is along y and density of state is along x. So when we plot this, we will get a parabolic curve, which is right. But in case of ferromagnetic material, we have a parabolic curve which is slightly shifted for upspin and downspin, such that at a certain the Fermi level, you will have a higher population of one particular spin, that is upspin, and a smaller population of other spin, that is downspin. Hello?
Yeah, fine, sir.
Yes.
Please continue.
Okay. So ideally, we would like something like this, where we have zero population of the opposite spin and all the population of a particular spin. So that state is generally called as half metallic in nature. So in the half metallic state, which has only a particular kind of electrons at a Fermi level, and since only the electrons which are in the Fermi level are, but in practice you'd have, but in practice you have only ferromagnetic materials which are in this way. So ideally, people are looking for 100% polarization. That is only one type of spin present at the Fermi level, right? So that is ideally half metallic state. So now, how do we induce polarization in a magnetic material? So in a non-magnetic, I should say non-magnetic material by spin injection. So basically, when you form a junction between two dissimilar elements, one of them is ferromagnetic and the other is non-magnetic. So one of them is ferromagnetic and other is non-magnetic. Then what happens is, if you pass, we apply a potential across that junction, then there will be electrical spin injection. So the we can say electrons can move from the ferromagnetic material to the non-magnetic material. So thereby creating a non-equilibrium in the non-magnetic material as well. So this, although this will be only for a small amount of time when you are passing the electrical current. When you are passing the electrical current by applying a positive potential to the non-magnetic material and negative potential to the ferromagnetic material, the electrons will start to travel and create a non-equilibrium here also. So this population will be increased in the non-magnetic material, and that is why there will be induced polarization, and that is represented generally by the difference between the upspin and downspin electrons at Fermi level. EF represents the Fermi level, and N represents the number of upspin and downspin electrons. So polarization is the difference between these two divided by the total number of electrons. So ideally, we would like to be having 100% spin polarization, but practically we get around 60% or 70%. Then spin relaxation. So this polarization that we have induced, that will not be, we can say this the polarization that we have induced in non-magnetic material, that will not be for indefinite amount of time. That will be for a short duration of time, and after a certain time the population will reach to equilibrium if we are not passing electrical current. So that is called as spin relaxation. So a spin relaxation refers to the process that bring an unbalanced population of spin states into equilibrium. So there are many mechanisms of spin relaxation that depend upon the type of material, or the type of non-magnetic material where we are creating the non-equilibrium. But this is more advanced, so I'll skip this as of now. So we'll come to the important aspect, which is the giant magneto-resistance. So what is the giant magneto-resistance, and what is the giant magneto-resistance device? So giant magneto-resistance device is made up of two ferromagnetic layers, which are separated by a non-magnetic material, which is also called a spin valve. So the name valve comes from that we can have two kinds of current flows. So just like a valve, you can open and close it to maintain the flow. We can say flow. That is why it's called a valve. So then in that device, which is the we can say a sandwich structure of two ferromagnetic materials separated by a spacer layer, we have this GMR, which is defined as, if you see, this is the structure that is there. So if you see here, the there can be an upspin electron or downspin electron. So when a particular spin will not scatter and the opposite spin will scatter, so this kind of structure is used for, we can say, this kind of structure exhibits the giant magneto-resistance property, which is the uh, magneto-resistance. It is basically the difference between anti-parallel and parallel states. So here it will become more clear. So here I am explaining a magnetic tunnel junction. So magnetic tunnel junction is consists of three layers. Then one is a tunnel barrier, and again a fixed layer. So there are three layers here. Out of these three layers, two are ferromagnetic in nature. So this layer is ferromagnetic, this is also ferromagnetic. In between you have a oxide layer. So this is also similar to the spin wall, only that we have replaced the oxide layer, or we can say we have replaced the non-magnetic layer with oxide layer. So in this kind of a structure, you have tunnel magnetoresistance. TMR stands for tunnel magnetoresistance. So when we see, there are three layers. So out of those three layers, we have one of them is the free layer. So that which I am showing by bidirectional arrows. So free layer is free to move, which is having low magnetic coercivity. So if you try to move this layer either by applying a external magnetic field or by a current, then you can move this layer because this is having low magnetic coercivity. There is one more layer that is fixed, which is having high magnetic coercivity. So which is a hard layer. So fixed layer is a hard magnetic layer and which cannot move. So if we somehow are able to change this magnetization orientation of the free layer, then we are able to change the resistance of this junction from anti-parallel to parallel. So if we see, so we have three layers. So this arrangement can be either parallel or anti-parallel. So if we are having a parallel anti-parallel arrangement, that is called as anti-parallel resistance. If we are having a parallel arrangement, we call it as parallel resistance. And the difference between these two will be divided by the parallel resistance. This is called as tunnel magneto-resistance. And normally the anti-parallel resistance is higher and the parallel resistance is lower because of more scattering in the anti-parallel case and less scattering in the parallel case. Okay, so this is the concept of magneto-resistance and how it happens. So basically this device, this exhibits magneto-resistance, and it if you see, it will have an anti-parallel resistance and a parallel resistance. Now parallel resistance can be turned to anti-parallel if you apply a current above certain threshold. So this is a curve between current and resistance. So we are passing the current in the same device and its own resistance is changing depending on the direction of current. So if I keep on applying current in certain direction, it will keep on increasing the obviously it will keep on increasing the current, but at a certain point, sorry, there is a delay in my laptop also. Okay. Okay. So as you keep on increasing the current, at a certain point the threshold will come, and then your anti-parallel will become parallel. So this so the figures has gone slightly, we can say, um, problematic because of actually I am using the LibreOffice. So we'll discuss more about how we change the state of magnetic tunnel junction from the parallel state to the anti-parallel state. So this is done basically by spin transfer torque. So spin polarized electrons can change the nanomagnetic magnetization. This was discovered by John Slavinsky in 1996. So nanomagnet, we are using small nanoscale layers of magnetic material. So these are also called as nanomagnets. So this on this spin transfer torque, a surge of experiment is going on, and people are trying to get achieve uh, spin transfer torque at lower and lower currents. So lower currents means low powers. So if you we can say that Now, let us understand first what is the spin transfer torque effect, or we can say spin transfer torque curve. So, the magnetic moment, basically M for any ferromagnetic layer, M revolves around the effective field. So H effective is the total magnetic field that is there. So if there is no external field, this will be only the its own intrinsic magnetic field. So the magnetic moment, or we can say magnetization, it revolves around this H effective. So if you we can say suppose you have a magnetic material, and so you must have heard about the torque on a magnetic dipole. So if H effective and M are misaligned, then there will be a torque on it which is called as M cross H effective. So M cross H effective torque will always be there, and that will be towards this tangential in nature, which is gyromagnetic torque. So M cross H effective will always be inside the plane, and it's called as a gyromagnetic torque. Then since now one more torque that is always there is damping. For example, this is because if you have M and H effective and M is misaligned from H effective, so this will follow a helical path, and at the end it will get aligned with the H effective. So there is a damping torque and a gyromagnetic torque, and followed by there is a spin torque. So this spin torque comes from the additional current that you are passing. So when you are passing the current in the magnetic tunnel junction, you will get one more torque which is called the spin torque. So spin torque is due to the electrons that are being transmitted into the ferromagnetic layer. So once the spin torque and damping torque are balanced, this gyromagnetic torque will keep its motion, and there will be a circular motion of the electron. So you can see in these points, the magnetic moment will precess, and finally M will become parallel to H effective if you have damping greater than the spin torque. So if you are not passing sufficient current, then the spin torque will be weak, and the M will keep its alignment along H effective at the we can say eventually. Now, if you have damping is equals to spin torque, then this M will keep on circle. We can say moving in a circular path along H. So that is a we can say sustained oscillations are present. And when we have spin torque greater than damping, then this angle will keep on increasing, and you will get this magnetization is turned. So this is what happens in a spin transfer torque based magnetic tunnel junction. When you apply the current, if it is above threshold value, then you can turn the magnetization from here to here. But if it is not above threshold value, then the magnetization will remain in around along H effective. So this is basically governed by the LLG equation. So you can see that dm by dt means the movement of magnetization with respect to time. Consists of basically three terms, which is the GM torque, or I have written simply torque here. So this is the same GM torque in our previous figure. So this GM torque is the torque here, the first term. Then you have the damping torque, which is having direction in towards the center or towards the edge effective. And then you have the spin torque, which is opposite to damping. This depends upon the spin polarization of the current. So, so magnetization dynamics of any ferromagnetic material In the absence of current, you will have only two terms, which is damping and the gyromagnetic torque. But if you have current, then you have a spin torque will introduce one more term, and you can change the magnetization state from, we can say, along H effective to the anti-parallel to H effective. So this is the entire process. So if you see, here, you have a fixed layer and a free layer. Though fixed layer magnetization is always fixed, free layer magnetization can change depending on the incident current, or we can say incident electrons. So, so this process is very much like a, uh, we can say, this process basically involves transfer of spin angular momentum. So I can give you an analogy to understand this. You have a small ball and a big ball. So a big ball of high mass and a small ball of low mass. And so this is similar to this. Big ball is similar to the fixed layer, and small ball is similar to the free layer. So when you hit a small ball with a big ball, then what happens? Basically, when they collide, the momentum transfer takes place, and the big ball, when it is moving towards the small ball and it hits the small ball, it will hit. There is a collision, then big ball may stop and small ball will move with an even higher velocity. So this process, we can apply this process here. So fixed layer basically creates a spin polarized population of electrons when they are incident, or when you pass a current in this direction, which is the opposite direction. So incident electrons basically change the magnetization of the free layer by the spin transfer torque effect, which we we just seen. Now there is one more thing. If we have a small ball and a big ball, but if I move the small ball with very high velocity, so normally the small ball will hit the big ball and the small ball itself will be reflected back. But if you have small ball with very high velocity, you can hit the big ball and big ball may also start moving. So it all depends upon the momentum, because exchange of momentum is taking place in both cases, the collision between two walls and in this device. So whenever the current is passed in the opposite direction, the incident electron will go through, but some of them will be reflected back, and these reflected electrons will move the free layer. So basically, when we try to move a big ball with a small ball, then the small ball itself is reflected back in the opposite direction, and this is what is happening. So electrons will keep on moving, and reflected electrons will again exchange spin angular momentum with the with the free layer, and it will move in the opposite direction. So in this way, we can move from this to this and this to this, or we can say parallel to anti-parallel and anti-parallel to parallel. So both, we can say, operations are possible, and it all depends upon the amount of current that you pass. So let us go back to that figure. Yes. So you can see that if I pass a current which is greater than threshold, HLO is the high to low threshold. If it is greater than threshold, then I can change from anti-parallel state to the parallel state. And if I pass a current in the opposite direction, I can change from the parallel state to the anti-parallel state. This is the hysteresis that is going on in a magnetic tunnel junction. And since this low to high operation is going to be done by the reflected electrons, generally the low to high threshold is higher than the high to low threshold. So this figure, this is equal, but in practice you have higher threshold for low to high switching. So when the switching is done from this anti-parallel to parallel state, is going to be slightly difficult. Okay. So next is the spin wall devices. Some more devices that we will discuss now. Although these are not used much, but the concept is important if we are trying to design a completely spin-based system. So you have a local spin wall and a non-local spin wall. So in the local spin wall, what we have is two ferromagnetic materials that are separated by a channel, which is non-magnetic in nature. So E1 and E2 are ferromagnetic, and the channel is non-magnetic in nature. So when we pass an electric current, this current is between E1 and E2. So this current is basically due to the electric field setup between E1 and E2, and that is called the spin polarized current, and it will basically be a drift current. Now, similarly, we have this situation where we have a ferromagnetic injector and then a channel. Contact will be there. We can say small oxide layer will be there. Then we have a channel, and then one more ferromagnet is there at the detector. So when we are passing a current in between this, then there is a spin polarized population that is developed here that will move in this direction because of spin diffusion. So diffusion is something that takes place whenever there is a concentration gradient. So here we have developed a concentration gradient, and then it is allowed to pass and hit a target layer and change its magnetization orientation. So basically, uh, this can be used for storing information similar to the magnetic tunnel. So let us see how this really happens, and let us see a little bit of practical application now. Instead of going any deeper, let us discuss about a practical application. So the most important practical application is the memory application, right, of the spintronic devices. So basically, I will discuss briefly about this spin transfer torque-based magneto-resistive random access memories or magneto-resistive memories. So, as I told you that magneto-resistive memories, these have magnetic tunnel junction. So, magnetic tunnel junction is basically the data storage entity. For example, in a DRAM, you have capacitor and a NMOS, or we can say capacitor and a MOSFET. So, you have two devices where capacitor is a data storing entity, Now, in in MRAM, or we can say magnetoresistive memory, you have this magnetic tunnel junction as the data storage entity. And so this is conventionally this we generally show only three layers, but it's actually made up of more thin layers. So to keep the fixed layer always fixed, we have some antiferromagnetic pinning layer. So fixed layer is fixed by the exchange interaction between these two layers. So basically, this whenever the orientation or magnetization between the fixed and the free layer is parallel, the resistance is called as RP, which is low, and whenever the orientation is anti-parallel, the resistance is higher, which is called as RAP or R anti-parallel. So this is ideal to store data, because if you see that, let us say RP represents binary 0 and RAP represents binary 1, then we can this is like binary values are being stored, which can be stored for indefinite amount of time, because magnetization of any ferromagnetic material can be retained for almost 10 years. So you can basically store in a non-volatile way. So this I will we have already discussed how the magnetization changes. So I'll just go to MRAMs. So MRAM structure consists of one magnetic tunnel junction and one MOSFET, or we can say NMOS device. So you can see that in the we can say in the 90s we were mostly having the field right MRAMs. So and 90s and early 2000s we have only field right MRAMs. Field right MRAMs means the you used we can say we have a bit line and a source line. So bit line is connected to the drain of the transistor, and then the source line is connected to the source of the transistor. But there is an additional right word line. So this conductor was there. This conductor was used to generate magnetic field, which will change the free layer of the uh, magnetic tunnel junction, and data will be used. Data will be changed by magnetic field, and that is why it was called as a field right diagram. But that was having a lot of power consumption, because uh, this conductor was going to consume a lot of power to generate the magnetic field. So that is why, after the discovery of the spin transfer torque effect in 1996, people started to use the we can say the spin transfer torque based MRAM, which are called as STT MRAM. The spin transfer torque STT stands for spin transfer torque. So what is happening is here is we can do away with the right word line. So instead of right word line, you can remove this right word line. And now what you can do is you can perform the operation by current. So instead of having right word line, you will have only bit line, source line, and word line. So only three lines will be there, and they will be used for changing the state from parallel to anti-parallel. So here arrows are not visible, but I will tell you. So when you pass a current from in this red direction, so red direction means from source line to bit line, then the your orientation will turn from anti-parallel to parallel. And if you pass a current from bit line to source line, then the orientation will change from parallel to anti-parallel. So this is what happens in the right operation of this MRAM. Now, so you must be wondering how to perform read operation. So read operation is basically done by using passing a small current, sense current, that is passed through the cell, that is magnetic tunnel junction and the CMOS transistor, and is compared with a reference current. So reference cell will have the average resistance of the parallel and anti-parallel resistance, and this will be compared with either parallel or anti-parallel, whichever direction this state of MTJS. Okay, so this is the read operation which is compared by a sense amplifier, and output will give you the data. So now one more thing, that magnetic tunnel junction is basically I am showing again and again between these two blue lines. So these two blue lines are basically metal interconnects in between which this magnetic tunnel junction is fabricated at the back end of line CMOS processing. So when we can say in modern CMOS devices there are high number of metal layers, around 11 and above. So 15-20 metal layers are there. So in between two successive metal layers, let us say metal layer 12 and 13, you will have a processing of uh, magnetic tunnel junction, which will involve the basically a thin layer of ferromagnetic materials and non-magnetic materials, which will constitute a magnetic tunnel junction. So this is how it is fabricated in a lab, or we can say in an industry. So there are different kinds of parameters which are there uh, in a spin transfer of MRAM. So these are, we can say, write margin, write error rate, then read margin, read voltage, and read disturb rate. So these, all these parameters basically are used to characterize the one cell of STT-MRAM. One cell means one magnetic tunnel junction and one CMOS, or we can say one NMOS. So one transistor and one MTJ, one cell will have all these characteristics, and we will use them to characterize a one transistor, one MTJ cell. So, so these mathematical expressions are there, which we can discuss later. Now, how do you generally work on any spintronic based technology, and how do you plan to do it in your we can say lab? So there we have TCAD simulator that is used for doing the CMOS device. Then you have, because we don't have the models available in conventional simulators like Spice and other, we have to develop models. So Verilog model is used for magnetic tunnel junction, which basically implements the equivalent circuit of a MOSFET, or sorry, of a magnetic tunnel. So its equivalent circuit, it has to be basically, but the equivalent circuit is a, say, approximate model that should be calibrated, and it should be calibrated by using micromagnetic simulations and a tunnel resistance model. So, so if you have all this, you can simulate magnetic tunnel junction and CMOS, and basically spin transfer torque MRAM can be simulated. So all this constitutes a simulation methodology, and let's discuss about how we compare or with the three we can say technologies which are already existing. So SRAM has been this is the fastest memory that we have, and then DRAM is commonly used as main memory. So whenever you say that you have 8 GB of RAM in your system, then that is generally a DRAM. So, and whenever you say that I have 3 megabytes of cache in my, generally SRAM. So cache is generally SRAM, main memory is DRAM, and we can compare it with the STT-MRAM. So write current in SRAM is the lowest. SRAM is also the fastest memory. It is also having currently the low power. But DRAM, you can see that is quite high, and STT-MRAM is between SRAM and DRAM. The write operation also is comparable to DRAM. So as of now, we can currently replace DRAM with STM-RAM in next we can say 5 to 10 years. So it is a there is advantage that is there, that is in terms of non-volatility. So you can see that this is non-volatile, others are volatile, and there is cost overhead is also very much small in case of STT-MRAM, because only back end of line processing is there, and you can integrate a magnetic tunnel junction above CMOS. So you are not losing any area. So in case of DRAM also you will lose some area because of your fabricated MOS capacitor, and in case of SRAM also you will have area overhead because there are 6 transistors in a single SRAM cell. So that is why there is a large area overhead. But in case of STT RAM you have no area overhead. Standard there is a leakage current in SRAM because of 6 transistor all may be in we can say uh, there can be a drain leakage that can be there, drain to source leakage in the SRAM. And DRAM have a large standby power because of the refresh rate that they have to refresh in every 1 millisecond. So that is why you have a large, we can say, overhead or standby power. But STT-MRAM has a zero standby power. Even if you turn off the power, and you can have the data retained, and as and when you turn on the power, you will get the data immediately. So that is the advantage. And also there is no refresh in case of STT-MRAM. So you can store the data up to 10 years. So these are the important, we can say, comparisons between the RAM and other memory technologies. So with this, I will conclude my presentation. And there are several challenges ahead, which you can look at it. But this is only, uh, we can say, useful from a research point of view. So that's it from my side. If you have any questions, please ask.
Sir, any tools available to do the simulation work on the Spintronics? Open source.
Yes, yes. Open source simulation tools are available. If let me just show you some
Can you say
websites.
something about the tools?
Yes, yes, yes. Basically, object-oriented microwave framework is one of the tools that is open source and that can use for simulating magnetic tunnel.
Voice is not clear
But
actually.
it is more basically
Voice is not
yes,
clear, Dr. Shivam. Voice is not.
voice is not clear.
Uh,
Okay, but I not change anything. Hello. Am I audible?
uh, there is a disturbance.
Oh, it's in disturbance. Am I audible now?
No, not yet.
Okay. I don't know. It's, maybe internet speed has fluctuated. Hello.
Yeah.
So maybe I'll turn on the camera. Hello.
Ah. Yes, sir. Tell me, what about the open source tools on these Spintronics simulations?
Yes. Yes. Basically, so we have a object-oriented micromagnetic framework which you can use. So this, if you are able to see my screen, I can just show you. So this software OMMF by NIST, this is open source software that can be used by you, and there are now it has become quite not user friendly, but there are a lot of tutorials available now. Previously, it was having a lot of problems, but now it has been improved somewhat. So you can use this tool. This is for simulation of micromagnetic devices, or we can say spintronic devices also, with some modifications. So this can be used. Is completely open source.
So there is one question from the participants. They are asking about the power consumption.
Yes. Active power consumption as of now is comparable with DRAM, but it is higher than SRAM. Uh, and standby power, it is mostly the standby power that we are in benefit, and because there is zero standby power in STTM RAM, and also there is non-volatility. Because in DRAM, if you turn off the power, you will get your data will be lost. But in STTM RAM, you turn power back on, your data will be there. So that is the advantage. So standby power is zero, but active power as of now it is greater than SRAM but less than DRAM.
Okay, there is a question from Prakash. He is asking about the life and cost of STT memory.
Yes, life as of now is 10 years. Means 10, until 10 years you can retain the data. But cost as of now is high because it is only an it is not we can say cost per bit is high as compared to DRAM and also SRAM. So as of now cost per bit is high, and but people are research is going on to reduce the cost per bit.
Okay, so there is one more question from Shalva Kumar. He is asking that is this applicable only for memory design, or we can go for logic circuits?
Yes, people are developing logic circuits also. So it is applicable for logic circuits also. But logic circuits, you have to not only means they cannot be used directly. You have to either use with CMOS, or you have to develop some other devices which are completely spintronic based. So there are two ways people are working basically. Either they are using both CMOS and a magnetic tunnel junction, or people are working towards new devices which are all spin logic based devices.
Uh,
So new devices are basically to replace CMOS. So so there are two strategies of working: either replace CMOS or work with CMOS.
okay, so that is about the today's session. I invite Chandrasekhar sir. Will you please conclude the session?
Okay. Good afternoon. Hope this session was good and knowledge gainable. I extend my heartfelt thanks to all the participants and the speaker, Dr. Shivam Verma sir. Thank you for spending your valuable time. We will send the certificates in the evening. We hope you all support us for our future programs as well. Keep in touch. Thank you and stay safe.
Thank you, sir. Thank you, Dr. Shivam. You can leave the session.
Okay, thank you very much. Thanks for listening.
అంటే వెంటనే చేసినాం సార్ 11 వరకు 12:30 వరకు కొంతమంది ఎక్కువ సార్లు పెట్టుకుంటే 1 గంట అయింది కొంతమంది టైం పెట్టుకుంటే కరెక్ట్ 12:30
లింక్ పంపించాను.
చాలా రిక్వెస్ట్ చెప్తూ చాలా రిక్వెస్ట్ సార్ ఫీడ్బ్యాక్ ఫామ్ ఫిల్అప్ చేయండి సార్ కాపీ చేసుకొని
Provide feedback. To fill feedback over.